All right, this is supposed to be the title slide, but I will start with the talk, with the paper that I worked on with Rohini. But before I start, since this is a very special kind of workshop, let me say a few words of how this paper came into fruition, and that is going to tell you more about Rohini as a person. So it started after SUSY, one of the SUSY conference that took place in TIFR, and there was a hard session. Hard session means it's a repetitive derivative physics, and I got annoyed. I got out of it, and I met Rohini. I told her this is mindless phenomenology, and as you know, she's a no-nonsense person, and she would not take this silliness from me, right? And I had what I deserved, and right after that, she said, "Get down from your high horses and do something useful like." Try to find the tagger with jets where top decays leptonically. Okay. Now, before I start, let me just mention that was not the only time, since my silliness doesn't know any bound, and Rohini was always there with her sticks. Okay. So here's the problem. So I'll go very fast with this. The problem is you tag a boosted top, meaning that boosted here means that it's all the decay products comes within, let's say, a jet. Okay. Now, if you want to tag a hadronic top where all the decay products are hadron, that's easier because everything you observe, there are various scales, a lot of jet shapes you can construct. If you want to do the decay products where there is a muon, that's also easy because there is a muon spectrometer in our experiments, which are pretty clean, and having a muon coincided with a jet, it's also easy. Electron is hard, right? Because they also have their own shower, and the shower overlaps with the bottom shower. So that was the problem. So the way we say it, well, we'll make this tagger, but the condition that we set, because we wanted a tagger for an object, we would not use event information like missing energy. Okay? We'll only use whatever is available inside a jet. Okay, and just to make our life more miserable, what we decided, a lot of the variables that people come up with, often they have kinematic information. Top jets, 175 GeV, that has a very different kinematic property. So we said, well, whatever we do at the end of the day, we'll basically make sure that we get good efficiency by comparing ourselves with a fictitious jet which is around 200 GeV. Top also has a large missing ET inside the jet, but the origin of the met is different. Okay, so that was the premise, and I'll go very quick from here. So the procedure is really simple, right? You first identify, you have lots of jets, identify what you call an interesting jet. For example, a jet with a large amount of energy in the EM cal is an interesting jet. Then once you have identified an interesting jet, what you do is say that which portion of your jet is electromagnetic rich, right? You do that by declustering jets in the usual sense. Here, and we give an algorithm how to find it, prune it, find only the necessary pieces out of it, and you find your electron candidate. So I start with a jet, then I identify what are the portion my guess is for an electron inside, and the rest of it is what my B is, right? So I basically have a B, and I have what is the rest minus the electron and an electron. Okay. Now that's not sufficient. You have to do something more, and here comes the answers that whatever energy configurations I have, the answers is that there exists a massless 4 vector, which when added to electron gives me a W, and the which added to the B and an E gives me a top, right? And the condition is, because of collinearity, is that the massless 4 vector has to lie within the jet. Okay. Once you put yourself through this, you propose certain variables which has definitive expressions if it is really a top jet, and not these things if these are not. Okay. You have everything, then you turn the crank, put everything into different stuff, and we know this very well, produce plots after plots, do a tagging, find efficiencies, and things like that. So that's basically what that paper was. Okay. Now, let me move on to talk about something else. So this is, the title is AMSB+SQCD, deep dive, and what I mean by this, okay, so let me give you a context. So what do I observe? I observed hadrons, okay. What do I know very well is the QCD Lagrangian in terms of weakly coupled quarks and gluon, which we have tested very well at high energy. Going from here to here is difficult route, right? And so the way we go there is typically often uses various effective field theories like HQET, inner QCD, chiral Lagrangian, or you put it on a computer, right? And they also talk among each other. So that's the standard way that we try to understand our long distance physics, starting with, let's say, a very, very short distance Lagrangian, okay? And while we are doing this, we use various generic tools like large N limit, QCD sum rules. All of these are good. And here's the put into context. What I'm talking about, this tool is AMSB+SQCD, is what I view it as like a tool that to be compared with the other that exists, okay? So that's what it is. And this talk is about that. And what I will try to show you in next few minutes, give a broad picture of what that is. And doing this, it's not just a math for the sake of doing math. Doing that, it's not going to yield a QCD. It's going to yield QCD-like theory. But doing that, it gives you a lot of intuition. And you take that intuition back and do a lot more with our real world. Okay? So that's what the cadence. So I don't think I need to explain this over here, but still give me 2 minutes. You start with an SQCD. Great thing about SQCD is supersymmetric QCD, let's say, SUN theory, is that the IR is exactly known, okay? So for example, degrees of freedom at very, very low energies are the mesons, the quark and anti-quark, the Q and Q bar, these are fundamentals. FR gives you the number of flavors, okay? And AM gives you the low energy degrees of freedom where color is contracted, and the indices of AM basically indices of flavor. Okay, it's a matrix, right? Now, more than a last century, Affleck-Dine and Seiberg calculated the nonperturbative potential in the case of F is less than N. Okay, and it's exact, right? And the main thing that you get from here, the field that I talked about is over here. It's the determinant of M. And this lambda that shows up is very analogous to the QCD scale, right? It's the holomorphic. This is supersymmetry, SQCD. No, SQCD, last century physics. N equal to 1. Yeah, okay. Very good. So, and this is the holomorphic scale, which broadly speaking, you can compare it to our QCD. Okay. So one thing you get from here, that if you derive the potential from this superpotential, determinant come in the denominator. So it basically goes to 0 in the limit where M goes to, determinant M goes to infinity. It has a runaway vacuum, easy to show. Again, very, very old physics. Now, they did the Seibergology basically refers, they did it for the whole spectrum for different values of M. Seiberg and his collaborator, they classified how the IR looks like. Okay, all right. Now comes the AMSB+SQCD, but before that, one would think, since I know SQCD, maybe I'll put a little bit of SUSY breaking. So below the SUSY breaking scale, therefore I get my my QCD, and I will be able to have a lot more information about the strongly coupled QCD, because I'm starting with an exactly solved SQCD. That turns out it is difficult. The main reason it is difficult, because whichever way you try to put the SUSY breaking information, it modifies your spectra. It modifies in terms of how SUSY breaking is communicated, how SUSY is broken. All sorts of information sips into that. Okay, it's not, you can't decouple that. It's very, very dependent on the UV constructions. Okay, that's where the AMSB becomes great tool, because this is one of the things which is completely UV independent. Okay, it's entirely given in terms of low energy beta functions, low energy certain mass parameters, and so on and so forth. And we understand this because this is really what we have been doing for last 20 years in the context of finding supersymmetry at MSSM. Of course, we are trying to look at a very different problem, but we understand this AMSB part, right? Okay, so what Hitoshi and collaborator did, I haven't yet come here, right? Also, I already talked, it's UV sensitive. What Hitoshi and So let me put what AMSB does. There's one slide of how it works out. Let me not dwell too much. The main thing is the fact that the SUSY is broken is communicated via something called a chiral compensator. Okay, so this is the phi field. It is like it is completely a chiral field, but you see the theta square M field. This M is the gravitino mass, and this is what parameterizes the SUSY breaking. So at the end of the day, you take M equal to 0, you basically go back your SQCD result, and you take M away from 0, and you have a SUSY breaking coming in. You have a particle and S particle splitting up. If you want to generate what the scalar potential looks like, it's complicated, but this is a formula. Okay, so this is the stuff. As you said, we made our life calculating the gluinos, quark masses, lepton masses, all sorts of things in all sorts of mediation, and AMSB was one of them, right? As I said, we understand the hell out of this. Okay, so what Hitoshi and collaborators did is that they took the SQCD, they perturbed it by having a little bit of AMSB breaking, and what they found is that what it used to be the ADS potential, which has a runaway far away, that gathers a minima. Okay, and it gets stabilized at a particular value which is dependent on this SUSY breaking scale L. Okay, so that was a non-trivial exercise. So the story, if you now take this, what does it mean in terms of a spectrum? If I take M to 0, then I will have mesons and mesinos, glue balls and gluino balls, the baryon and S baryon, all sorts of tower. The moment you include M here, little bit of SUSY breaking, what you see that the spectrum opens up in all these different sides. Okay, you can take this. So Hitoshi's limit is M. He takes M all the way above lambda. I don't think I even believe that part, but that is okay. But the thing is, below this, you still have QCD-like theory. Okay, that's it. IR is QCD-like theory. So you do this exercise and see what you learn. Okay, so Chabachaki and his companies and Hitoshi Murayama and other companies, they worked out again just like the same exercise. Yeah, so all of them, the gap is scales with M. Yes, so you push M up, you raise the gap up. What do you mean completely different? It is completely fixed. So what problem comes in when you take M above lambda, the one worry you might have. Yes. It is roughly given like M by 16 pi square, roughly, for example. Yes. So, pretty small, yeah. But, yeah. I will talk a little bit about them. Actually, that statement was more about the glue balls and the baryons. It turns out that if you take the mesinos from here, you actually get order lambda. It's some function of lambda and M. But I'll come to that. I'll show some part of it. Okay. Okay. But the statement of the particle spectrum, that being deviated by something like an M by 16 pi square. It's a one loop piece. M square goes as M square by 16 pi square. But that's all. The glue balls will be pushed above. Yeah, yes, I agree. But so far, as you say, for F less than N, for example, it only makes statement about, for example, these mesons, the pions, right? So I will stick there. I'll come. Baryons, because. No, that is my typo. I'm sorry. I'm sorry. But we should have known from Suzy. I'm sorry. Okay, it's a great observation. This should be the other way around. The S baryon should be above. Thank you. Thank you. Okay. All right, so they chalked out the whole theory from left to right, where you have a, you showed like the full for, you say get QCD-like spectrum for all ranges of F. Okay, so now here we come in. In rest, let's say 10 minutes, I will try to get to the point. So one thing that you realize is that what more can I say? So first you look at what is the non-perturbative potential. The non-perturbative potential is determinant of M, and you could ask the question, what the hell is, determinant of M? To ask that question, you go back to now standard model and chi-PT. Okay, so in chi-PT, like SUN cross SUN broken, or UN cross UN broken down to diagonal U1, correspondingly you get 9 Goldstone bosons, right? But the symmetries are not exact. They are broken down by the mass term explicitly and by the QCD anomaly. Okay, chiral anomaly by QCD. Okay, so what you get is 9 pseudo Goldstone boson. So the way to express them is by the exponentially nonlinear realization, where you take all the direction in the coset space, and correspondingly each direction you add an excitation. Okay, so this is how it's written as. So the T's are the generators in the broken direction, and the pi's here, these are 8 of those, and one of them is the eta prime. Those are the excitation around the broken direction, right? T0 is the identity element that corresponds to the broken E1 axial. Okay. Once I have that, you realize determinant of U is nothing but your eta prime. Okay. So that's great, because whatever non-perturbative thing we have written down is actually a polynomial of eta prime, which makes sense because we know how eta prime gets mass, eta prime gets polynomial, so it's completely falls in line. Okay, so that's wonderful news. And so what you find here, now expanding the whole potential include the mass terms of the quarks as well, you find the full potential that has eta prime. Okay, you discuss about or think about the branch-like structure in the potentials and compare with the standard model, what the branch-like structure you get, all sorts of things. And more importantly, now you can think of like you have a different limit. Large N limit used to give you what the eta prime potential used to look like in standard model. And now you have an AMSB+SQCD limit, which gives you what the potential looks like. Now you literally have another pivot. Okay, putting this together, you scratch your head a bit and you just write down the potential for eta prime. Okay, so that's a non-trivial potential which at large N becomes the Witten's term. Okay, done with that. But we can do more. I mean, if you look carefully, this involves determinant of U, which has the eta prime, but this has the U itself, so it basically has all other pies. So not just this is the potential of the eta prime, it also has the potential of pi. So you might as well come and try deriving the chi-PT. Okay, this is what you can do to amuse yourself. We did, like for example, calculate the spectrum, pi 0, pi plus and stuff, and you get the standard results, like how it depends linearly with the masses. You find what is the k0 k plus mass difference looks like, what's the Gell-Mann-Okubo mass relationship looks like, all sorts of things. The angle between eta prime, pi eta prime, all sorts of things you can keep doing. Okay. You can even go, since you have the exact potential, you can go and just solve what the waves look like, okay? What the chiral symmetry breaking waves looks like, which would correspond to the condensates, right? You find, for example, if which is d bar d wave divided by u bar u wave, which sort of looks like a difference, which is 1, isospin limit, then is a difference mq, which is a difference of mu minus md suppressed by the strange quark mass, which is what we have also in chi-PT. Okay, as I said, you can do many things. You can get lepton form factor, hadronic form factors, all sorts of stuff, but we're doing something amazing. What we thought, okay, let's go and put 4th generation below lambda QCD, okay, solve everything, and then take the 4th generation quark mass analytically beyond lambda, right? So as you take it beyond lambda, you have a sliding scale. Now you actually start predicting what the charm physics starts to look like with the rest of the chi-PT. Okay, like for example, you find amusingly that eta prime and eta c start mixing with each other, and that mixing angle goes away as you take larger and larger charm mass. Okay, you find like the CC bar wave starts scaling with the charm. I'll be done. With the charm mass, and as large charm mass goes, it vanishes, right? But not all. So these are amazing facts. What it also teaches you, look, I can come with a weird sense where I see that if I start from a non-trivial weird theory which has nothing to do with QCD, and then I take few steps back, I start writing down theories that involves both light-like bound states, heavy light bound state, heavy bound states, okay, all in the same place, and relativistic, okay, which tells me not by starting with QCD, but there might exist, let's say, a phenomenological Lagrangian, a relativistic Lagrangian, which has all the bound state together, at least for the pseudoscalar part right now. That's what I'm considering right now, which in appropriate limit, it goes back to the HQET and our QCDs and the Cara Lagrangian. Okay, so this is basically the intuition. Okay, so can we do that? So let's start with in 2 minutes, let's try to do the same thing with the charge weak decays. See we can do it or not. It turns out we can. So I'll not take the SUSY part. That was the inspiration. Forget about SUSY. Let's go back to standard model, and let's be bold enough. Let's not think of failing and just try to write down Lagrangian involving fields that has creation and annihilation operators of one particle bound states. Okay, so you start doing it by understanding what the major symmetries are. You have the low energy SU3L cross SU3R. Let me now take MC equal to MB to start with, so I get an SU2L times SU2R for the heavy flavors. Okay, symmetry understood. Unfortunately, weak decay breaks it because CKM breaks it. Well, translate the CKM into spurions, so everything is manifest. All the symmetries are good. Start writing composite operators, quark composite, heavy composite, heavy light composite, and boldly go where no one has gone before, like designating the D field, B field, eta C's, and everything inside these composite fields. Okay, and then simply start writing operators. Done. Okay, so first let's look at the leptonic weak decays. You construct operators which looks like current for different generators. If you look at, like, for example, W exchange process, this is current interaction, right? And these currents are exactly the symmetry currents for various flavor. Okay, so you looking at that, how the fields transform, so you can construct the corresponding current. And so you can start looking, for example, for the leptonic current, marry them with one of those 12 pieces, and those gives you various leptonic transitions, leptonic decays. For the hadronic, you take square of those, but you can't stop. You can even construct the single traces. So here, these are traces over flavor. There also exist at the same order traces, single trace over all 4 fields. Okay. It turns out these are the things that basically gives rise to various effects which violates what is it called? I'm forgetting the term. I'll come back to it. Okay. So 1 minute I will describe what is the good thing about that. You can do various consistency check. Go to the HQET limit. Okay. Come with an ansatz like the decay constant scale with their masses. And you come with a prediction that, for example, the form factors scale appropriately with the masses of heavy quark. Okay, you can do a lot more. You can figure out, there used to be a puzzle where the eta prime rate from B was so much larger than the eta. It turns out, this is not BSM effect. This is SM. You just have to calculate it very correctly. But here it turns out it's easy to talk to me later, I'll explain it to you, or there are also slides over here, how this is very intuitively, it's easy to explain that, why they are far bigger than that. We constructed B to K pi, B to D pi, various isospin sum rules, all work out, and many more. Okay, running out of time, let me stop over here. So this is the summary. As I said, this is a limit of QCD. Utilize this limit. This is not a machinery for precision calculation. Don't go there. Okay, this is not about that. What it is about is, at least for me, is to generate intuition. okay, and transfer this phenomena. A lot of it is quite complicated in a language that it's easier to understand, at least for me. Okay, so that's the reason why I like it more. And I think we are poised so far. Whatever we are doing are stuff that are more or less understood, right? But you can do a lot more. You can understand various properties of the spectrum itself. Okay, I'll stop over here. Thanks.